The second video in our introductory chemistry unit, Tools of Chemistry, deals with accuracy, precision, and percent error. And you can see we have two learning targets here. First, we want to be able to describe the difference between accuracy and precision in measurements. And we also want to be able to calculate the error and percent error in a measurement or a series of measurements. And we'll be looking at both of those ideas here. Some resources here. Here are the text pages dealing with this material. A couple of videos here. One of them is on that first learning target. The second one gives you some examples on calculating errors and percent errors if you want some more examples of that. And then finally there's a practice worksheet here that I have found that you could access to work on your percent error calculations. Alright, so the difference between accuracy and precision. These are two terms that you've probably heard before. You've probably used them both before, I would guess, and you've probably used them to mean the same thing. The thing is, though, is accuracy and precision are not the same thing. That's the first thing we're going to jot down here. Accuracy and precision are not the same. They are not the same. We will give a definition for each of these. If a measurement is accurate, if we were talking about a measurement's accuracy, this probably is defined as you would expect it. You've probably used this term accurate or accuracy to mean what we want it to mean in chemistry. Accuracy refers to how close a measurement is to the accepted value. Anytime you see the term accepted value, you can think of that as being the right answer. We usually don't use the term the right answer, the correct answer, because as we'll discuss here moving forward, especially once we start learning about measurements in our next video, there is no such thing as an exact measurement. It doesn't exist. So you can think of the accepted value as what you should get if you do it correctly. So whenever we talk about a measurement being accurate, we mean that the measurement is close to what we should have gotten for the answer, or the right answer. So that's probably how you've always used that term accuracy before. The term precision or precise, if we talk about a measurement or measurements being precise, it is not the same thing as being accurate. Precision refers to how well a series of measurements agree with one another. In other words, this would apply to the idea of, let's say you're measuring the density of an unknown metal. Okay, and as part of your procedure, you do it 3 times. And this is something we do quite often in experiments. We want to run more than one trial. So you do 3 trials. And so at the end, you'll have 3 different answers, 3 different measurements. If those 3 measurements are all very close to each other, we would say that they are precise. If they are a ways apart from each other, they're not precise. So another way you can think about precision is consistency. Okay, the precision of measurements is about the consistency of the measurements, how close or how well they agree with each other. Now, under ideal conditions, we will have both accurate and precise measurements. To help us understand this idea of accuracy versus precision, we're just going to draw a few pictures here to help us get an idea of what we mean. And the pictures we're going to draw are of a target. Okay, so say you have an archer. And this is what a lot of the videos that you can find on accuracy and precision will show you. You have a target and showing you an archer shooting at this target. Let's say the archer shoots a single arrow, one arrow, and the archer hits the bullseye. I'm going to draw an X to represent that. This archer is accurate because the archer is close to the correct value where the archer would expect to hit if he had good accuracy. So we could say here the measurement, if you will, is accurate. We can't say anything about the precision, though, because we only did the measurement once, or the archer only shot one arrow. So we have no idea how consistent these measurements are. So I'm just going to put a question mark here for precise. We don't know. We have no idea. All right. Let's say, in another example, another target here. Here's our bullseye. That the archer does this. The archer shoots 3 arrows. They're all very close to each other, but they're not particularly close to the target. Well, because the archer did not get close to the bullseye, this is not accurate. Not accurate. However, the archer was precise because the measurements, if you will, agree with each other very well. This would be in a situation where you are very consistent with how you use a measuring device, but you simply use it wrong. Okay, maybe you're using a ruler and you're very consistent with where you line your eyes up, but your eyes aren't really directly over what you're trying to measure. Or you're using a graduated cylinder and you don't get to eye level with the meniscus on the graduated cylinder. So you might be very consistent with how you measure it, but you simply don't use it correctly. This would definitely lead to not accurate results, but could give you precise results. All right, let's say we had something like this, where the archer was not very close to the target, nor was the archer very consistent with the location of the arrows. This is obviously not accurate because none of the arrows have hit the bullseye. It's also not precise because the measurements, if you will, do not agree with each other. Okay, this is most likely to happen if you're using very poor technique using a measuring device. So you do it differently every time. The fact that you don't have good technique leads to very imprecise results, also leads to very inaccurate results. The obvious goal in any measurements would be to be both accurate and precise. So say an archer was always right around the bullseye, very close, if not in the bullseye every time. This would be accurate. This would also be precise. This is what we want to see with measurements. We want to be spot on as far as being close to the correct answer, and we should be able to take the same measurements and get very close to the same values each time. You're never going to get them exactly the same. That will never happen. But you can be very consistent and get results that are very close to each other. All right, so that's the difference between accuracy and precision. Let's jump down here and take a look at the first example question here, because this deals with accuracy and precision. We're told that 2 students measure the density of an unknown metal 3 times each. So they've each done 3 trials, and it gives us their data below. Student 1 gets these answers for the density, 6.34, 6.31, 6.30, all with the units gram per centimeter cubed. And student 2 gets values of 7.11, 7.19, and 7.12, also all grams per centimeter cubed. And we are told that the accepted value for the density of this metal, remember, think about accepted value as the right answer, is 7.08 grams per centimeter cubed. All right, first question. Which student was more accurate? Explain. Remember, accuracy refers to how close to the right answer the accepted value we get. Just looking at the values here, we can see that student 2 is much closer to the accepted value. Each of these measurements are much closer to 7.08 than that for student 1. So I'm going to write student 2 here, student 2, and as far as an explanation, the measurements are closer to the accepted value. And that is why student 2 is more accurate. Question B. Which student was more precise? Remember, precision has nothing to do with how close to the right answer we are. So the fact that student 2 was closer to the right answer, the accepted value, makes no difference. What we want to look at is how consistent the measurements are, how well the measurements agree. A great way to do that is to look at the range. In other words, the difference between the high value and the low value. If we look at student 1, their range, the high value is 6.34, the low value is 6.30. That's a range of 0.04, 4/100ths of a gram per centimeter cubed. We think about the same thing for student 2. The high value is 7.19, the low value is 7.11. That gives you a range of 0.08. So that right there would show us that student 1 was more precise because their values agree with each other much better. So student 1's measurements are more consistent. Student 1's measurements, they are more consistent. Okay, that is the difference between accuracy and precision. The second part of this lecture deals with a way that we can quantitatively measure our accuracy. Quantitatively meaning put numbers with it. We're going to go back up here to our key ideas. I'm just going to block off a little area here. That's the accuracy precision part. If we want to talk about an error, if we want to know the error in your measurement, the error in the measurement is equal to the measured value, so this is what you would get in the lab, minus the accepted value, what you should have gotten. The error, measured value minus the accepted value. Let's jump down here and take a look at example problem number 2, because we're asked to calculate an error. It says you measure the length of a wood block to be 28.65 centimeters. That's what you measure. That is your measured value. The actual length, or the accepted value, if you will, of the block is 29.94 centimeters. You're asked to determine your error and percent error. So we'll just do error for now because that's all we've looked at. Well, we know that the error is your measured value, just looking up at the equation we had before if you want to look back up there, your measured value of 28.65 centimeters minus the accepted value, what you should have gotten, of 29.94 centimeters. Notice your value is lower than the accepted value, which is going to give you a negative number. That's fine, because errors are often expressed in a way that tells us if we are too high or too low in our measurement. This should give you a value of negative 1.29 centimeters. So if we look at this, we look at our error, we know that we were low in our measurement, and we were low by 1.29 centimeters. So that is the error. The percent error is often something that's more useful to us than error, and you'll see why here in just a second. We're going to jump back up here to the key ideas. We're going to write another equation. Our percent error is equal to the absolute value of our error. Recall from what you've learned in math, this notation here with the two solid vertical lines is absolute value. That means the positive value of your number, really, or distance away from zero. You might think of it that way. It's the absolute value of your error divided by the accepted value that you should get times 100 to turn it into a percentage. So let's go down and take a look at how we would calculate our percent error for the example we're working on. Alright, jumping back down here. We are going to take the absolute value of our error. So the absolute value of negative 1.29 centimeters is just 1.29 centimeters. And we're going to divide by the accepted value, what we should have gotten. So that's the 29.94 centimeters. Don't divide by what you got. Okay, that's a common error. So don't divide by that. And then we're going to multiply by 100, turn it into a percentage. Let's see, plug this into the calculator here. I get 4.31%. Notice centimeters cancel here, turn it into a percentage by multiplying by 100. So this is our percent error. Now the reason why percent error is often more useful to us than error is because of this. Let me just give you an example. Say I told you you had an error in measurement of 5 centimeters. That was your error. Now, how good or bad that measurement is really based on what you're measuring. If, say, you're measuring the distance from Lake Mills to Forest City, then that error is really, really tiny because that's a much, much larger distance. 5 centimeters compared to what you're measuring is tiny. So you're going to have a very, very tiny percent error, meaning you were very, very accurate. But say you weren't measuring the distance from Lake Mills to Forest City. Say you were measuring the length of your index finger, and you were off by 5 centimeters. Then that is a ginormous error. In fact, depending on the length of your fingers, you could have something close to 100%, if not more, of a percent error, based on how long your finger is. So error alone can be useful for us, especially if we want to know if we're high or if we're low in our measurement, a positive or a negative number. Whereas percent error is really a better indication of how close we really are. We're not really concerned with how high or low. There is no such thing as a negative percent error. There will always be positive. But it can be a better indication of how accurate we are because it takes into account how big the value is that you're trying to measure. All right, we have one more example here. Flip over to the next page, and it says, determine the error and percent error for each series of measurements in question 1. Well, let's jump back to question 1 here real quick. That was with the 2 students and their density measurements. So if we have a series of measurements, we don't need to do the calculation for every individual one unless we want to or we're asked to do that. What we can do is we can do the calculations for the average of them. Okay, so back here on our question 3 here, I'm just going to jot down the values so we don't have to keep flipping back and forth. So student 1 had values of 6.34, 6.31, and 6.30 grams per centimeter cubed. And student 2 had the values of 7.11, 7.19, and 7.12 grams per centimeter cubed. And I also want to jot down the accepted value. That's also on here. The accepted value is 7.08 grams per centimeter cubed. All right, so now we have all of our data there that we need. We'll go back to answering the question. So the first thing I would want to do here is I would just want to find the average of each of these. So the average, recall we're just going to add up each of the measurements and then divide by the number of measurements that were taken. So for student 1, let's see what we get here. I get a value of 6.32. So the average for student 1 is 6.32 grams per centimeter cubed. I don't want to keep any more decimals than the measurements went to because that wouldn't make any more sense. Your calculator is going to tell you 6.316666 repeating. But I don't want to keep all those because it wouldn't make any sense if all of our measurements only went to the hundredths place as they do here. All right. For student number 2, let's find that average. 7.11 divided by 7.11 plus 7.19 plus 7.12. And I'll divide all that by 3. This gives you an average of 7.14 grams per centimeter cubed. All right, for student 1, I need to find the error and the percent error. Recall that we want to take, for the error, we want to do the measured value, and I'll just do the average, 6.32 grams per centimeter cubed, minus the accepted value of 7.08 grams per centimeter cubed. Notice this is going to give you a negative value. That's fine. That just means that we were low in the measurements. This is negative 0.76 grams per centimeter cubed. That is the error for student 1. Error 1. To do the percent error, I'm just going to take the absolute value of the error, so 0.76 grams per centimeter cubed, and I'm going to divide that by the accepted value of 7.08 grams per centimeter cubed, and multiply by 100. So 0.76 divided by 7.08 times 100. This gives me 11%. This is the percent error 1. Now I'll just do the same thing for student 2. Student 2's error, I want to take 7.14 grams per centimeter cubed minus 7.08 grams per centimeter cubed. This is going to give you a positive value, and for errors, we often want to be explicit about it and put the positive sign there. This is plus 0.06 grams per centimeter cubed. This is error 2. Okay, the common notation is to go ahead and put the plus sign there. I know it doesn't change the value any. In math, obviously, you probably wouldn't put it there. But with errors, oftentimes we will. So we can be explicit and says we are that much too high in our measurement. And then the percent error, I just want to take the absolute value of the error, so 0.06 grams per centimeter cubed, divided by the accepted value, 7.08, times 100. And this gives us, let's see here. Oh, got it plugged in right to my calculator. I get 0.8% error. And that is percent error 2. If I had asked you what student was more accurate, well, I know we already answered it before, but we can now see very clearly that student 2 was much more accurate. Their percent error is much lower than that for student 1, because percent error is really a measurement of the accuracy of the measurements. All right, the example problems are done. Next up, we have a couple of practice problems. This is a great time to pause the video, try to work the practice problems on your own, and then to see how you did. Because everything we've done here, we've already covered in the examples. All right, practice problem number 1. It says you measure the length of a wood block and obtain this value, and you're told the accepted value for the length of the block is 12.59. Calculate your error and percent error. Well, the error, that is the value that you measured, 12.65 centimeters, minus the value that is the accepted value, the right answer, 12.59 centimeters. This is going to give you 0.06 centimeters. And because it's a positive number, I am explicitly going to put the positive sign up there to show that we are too high. So that is the error in our measurement. Our percent error, we want to take the absolute value, obviously it's positive, so that's not going to change it any, of our error, divided by the accepted value of 12.59 centimeters times 100. So 0.06 divided by 12.59 times 100, I get 0.5%. And there we go. There's practice problem number 1. All right, number 2, looks like we have a series of measurements here. We're told in an experiment you determine the melting point of a substance 3 times. So we did 3 trials. For each of these trials, you get these values, 56.7, 58.1, and 53.9 degrees Celsius. And then we're given the accepted value of 55.2 degrees Celsius. It wants us to calculate the average of the 3 trials, the error, and the percent error of our determination. So the average, let's say a 56.7 and 58.1 and 53.9. So you add them up and divide that all by 3. I get 56.2 for the average. 56.2 degrees Celsius is our average. So that'll be the value that we use for our measured value in our calculations. So our error, 56.2 degrees Celsius minus 55.2 degrees Celsius. This is going to give you 1.0 degrees Celsius. And it's too large. It's a positive number, so I'm going to put the plus there. That is our error in the measurement. Our percent error, we just take our error, 1 degree Celsius, divided by the accepted value of 55.2 degrees Celsius times 100. So 1 divided by 55.2 times 100, I get 1.8%, and that is the percent error. And that is the end of our lecture.